Right, just to note, I skipped question 7 because we haven't covered it in class. Okay, I'll come back to question 7 at a later date. Okay, I'll promise you a video for question 7. Right, let's move on to question 8a. State two conditions required for a particle to experience a force in a magnetic field. Right, I'm just going to go over a rough recap of what we have covered so far. Right, if we think until the chapter magnetism, right, it's always been a magnetic field exerts a force on a magnet that sits inside the magnetic field. Alright, an electric field exerts a electric force on the electric charge sitting in the electric field. So for example, a positive charge in the electric field clearly experiences electric force. Right? A negative charge in the electric field also experiences electric force, but most likely opposite direction to positive charge if I put them at the same position. Right? But after magnetism, we realize in electromagnetism that somehow a magnetic field can exert a force on a current carrying conductor, which means that if there are charged particles moving in a certain direction and these charged particles sit in a magnetic field, right, somehow they experience a force, and the direction of force is given by Fleming's left-hand rule. Right. So what is the criterions for the particle to experience a force in a magnetic field? All right. So the particle must be firstly charged, right? Because as we have discussed earlier, that the particle must be charged so that it can constitute, when it moves, it can constitute current. Okay. Secondly, of course, the particle must be moving, right? Remember that in Fleming's left-hand rule, it is current carrying conductor experience a force when it sits in a magnetic field, right? So how to be current carrying? You must first have a charge and you must be moving. Those are the criteria for current, right? So if you're not charged and you're moving, then you're not current. If you are charged but you're not moving, again, you're not current because current requires the movement of charged particles. All right. Something a bit unique about this that maybe I never teach you in class. Okay, I'm going to teach you right here. Is that if this is the magnetic field, let's say the black direction is the magnetic field and the blue direction is, let's say, movement of positive charges. Right. What we learned in class is that if the movement of positive charges is in this blue arrow's direction and the magnetic field is upwards, okay, I can apply Fleming's left-hand rule here. Okay, you can just do it just for practice sake. Okay, your magnetic field is up, your third finger should be your current, right? And therefore your force at this point should be out of the screen or out of the paper, all right? In your syllabus, the angle between magnetic field and motion of the charge is always 90 degrees. However, in reality, that's not always the case. Let's say if the current moves in this direction, magnetic field is in this direction, right? Actually, there's still a force, right? And likewise, if I shift like that, there's still a force, right? Likewise, there's shift like that and like that, also got force, right? The only time when there's no force is when the current is anti-parallel to the magnetic field or parallel to the magnetic field. All right, so these are the only two conditions whereby there is a current when a charged particle is moving, right? But it's moving parallel to the magnetic field, no force. Okay, again, if the current is opposite in direction to the magnetic field, exactly opposite direction, again, no force. All right, therefore, the more generic answer for point 2 is the particle must be moving in a direction not parallel to the magnetic field. And this ensures that there is a force exerted on the charged particle moving. All right. So you may say, hey, teacher, this is not fair because we never learned this in class. And I would say that is true. In the context of the O levels, right? So far, I look at all the questions, right? They always give you like that. The magnetic field is always 90 degrees to the direction of the current. Of course, the current can be this way or this way, but it's still 90 degrees. Right? So if you had given something to the degree that the particle must be moving in a direction perpendicular to the magnetic field, I'm pretty sure, 95% sure, they will also give you the mark. Alright? So I think most of you would have written something like that, and you don't have to worry. Okay, the charged particle moving in the direction perpendicular to the magnetic field will probably get the second mark, full marks. Alright. Okay, we move on to part B. Gamma rays and a beam of fast-moving electrons enter a strong magnetic field, shown in figure 8.1. Right, uniform field into the page. Right, gamma rays and electrons moving this way. Magnetic field acts only in the shaded region. Okay, direction of magnetic field is into the page, right? So you need to get used to this kind of terminology. Sketch gamma rays and electrons in the magnetic field. Right, so what happens to them inside the magnetic field? Right, gamma rays are firstly, this question is called a synoptic question. Means to say that they test you multiple chapters in the same question, right? So this question looks like it's a magnetic field question, right? Then you have electrons moving. You think, hey, this is electromagnetism. But then when they add gamma rays, then these become electromagnetic waves, right? So if you're going to read your electromagnetic waves chapter, okay, page 275, all right, point 8 of properties of electromagnetic waves, you realize that gamma rays carry no charge. Right? So if gamma rays carry no charge, even though it's moving, does it constitute current? The answer is no. And therefore, the gamma rays is unaffected by the magnetic field. There is no force from Fleming's left-hand rule. Right? Therefore, gamma rays go straight. Hey, fast-moving electron, you should realize that electron move this way means current is opposite to the direction of fast-moving electron. Again, this is hypnotic because if you look at the current chapter, not current waves, sorry, this should be under chapter on current of electricity, right? Just cancel these waves, right? On page 322, right? You look at the difference between conventional current flow and electron flow, you realize that how the electron flows is opposite to how current flows, right? In physics, we always talk about current, right? So the third finger is talking about conventional current, and since electron flow this way, conventional current must be towards the left, right? So you apply your Fleming's left-hand rule, you should find that the force at this point upon entry is downwards, right? If the force at this point upon entry is downwards, then your curvature will look something like that, right? So something to note that I won't go into extra detail is that this thing actually is a circular path, right? The why exactly I will not go into it. All right.